You're listening to a podcast from 702. 702.
The Naked Scientist.
Time for The Naked Scientist. We take your science-related questions on 011 883 0702 and the WhatsApp line 072 702 1702. Dr. Chris Smith is with us. Happy Monday, Doctor. How are you doing?
Yeah, happy Monday as well. I was enjoying that conversation because my mind was ticking along thinking, well, the problem is that if you don't have enough power to produce ice, then you haven't got enough power to produce other things that need to be made and kept cold. And you're quite right to say that liquid nitrogen does freeze things very rapidly. It's about minus 200 degrees C.
So, okay, because for the way John looked at me, I was like, oh my gosh, did I get it wrong?
No, we when I've done stage shows and science shows and things in Johannesburg, we've often used liquid nitrogen in order to show people the effect of making things very cold very quickly. But the problem is this takes energy. It takes energy to make the liquid nitrogen. How do you get it? Well, the air is 4/5 nitrogen. So if you take a load of air out of the room and you squeeze it really hard under really high pressure, you push the spread out molecules, which are nitrogen, together, and they slowly condense to form a liquid, and it gets very hot. So you take that heat away, and that's where you're doing work. And that's why it gets hot, because you're doing work against it. So you get rid of the heat and it condenses into a colorless, bubbling liquid, which is at about minus 200 degrees. But to keep it that way, you've got to keep it in insulated vessels. And you've also got to make sure that you replenish your supply, because as soon as you warm it up, it evaporates. It turns back into a gas again, back in the atmosphere. And that means you're back to square one. So even if you don't have any ice and you say, well, I'll use liquid nitrogen, well, that's only a solution until you run out of liquid nitrogen. It really all comes down to energy. Everything that we do has an energy cost attached to it. And we have to, in this day and age, prioritize what do we want to divert our meager supplies of energy into, one thing or t'other.
Okay, I think that's explained it quite well. Let us go to the line.
Only quite well. I'm offended. I mean, I thought I did okay with that. What was wrong with that?
I think the South African version of quite well and the British version of quite well are not the same. Conversation for another day, because how we use our language, not the same. I stand to be corrected. Let's go to Andrew in Hammanskraal. Andrew, go ahead.
Hello, Levo.
Andrew, you're quite welcome to the show.
Thank you, Dr. Chris. Dr. Chris, some 50 years or so ago, NASA sent Voyager 2 into space. Are they still in contact with it?
Hi, Andrew. Yes, Voyager 1 and Voyager 2 remain active. And the reason that, despite the fact that many decades have gone by since their launch, that we can still talk to them is because they're powered by radioactivity. They have a thermoelectric generator in them where a chunk of radioactive material, I think they've got plutonium in them, and this is radioactively active, so it's degrading all the time, breaking down, spitting out radiation, but in the course of doing that, it gets very hot. So you can use that heat to drive a thing called a thermoelectric generator. This is a material which has a hot side, you put energy into that side, and a cold side, which is the side that's pointing into deep space where it's very, very cold. And because of the arrival of the heat and the cold, and the difference between the hot side and the cold side, you can push electrons through it and you get a potential difference. And so you get a voltage. And these probes, despite the fact that they've been in space for decades, are still powered up. The intensity of the radioactive supply, though, is diminishing now because it is much older. And as a result, it can't sustain the same output of current that it did when the probes were first launched. So a number of systems have had to be disabled. And I gather that this includes some of the monitoring systems, but the transmitters and receivers are still working. And so periodically messages are sent to and from the Voyager probes. And it takes more than a day to get the reply back now because they are so far away. They are judged to have left our solar system. They've gone across the heliopause where the radiation pressure from our sun is pushing against the incoming radiation from into a solar space. And so they are now in no man's land in our galaxy between our star and the next star.
Thank you so much for that question. Let's go to Taz in Randburg. Hi, Taz.
Hi. My 7-year-old wants to know how is atoms formed.
Hi, Taz. And hello, what's the name of your 7-year-old?
His name is Raiz. Do you mind if I pass the phone to him?
Go
Because
ahead,
he'd really
Taz.
like to say. 1 second. There you go, Raiz. Hello.
Hi, Riz. How are
Hi.
you?
I'm okay, and you?
Good. You've got a question for the good doctor.
How do atoms form?
Right. Okay. Well, if we step back and say, well, what does the word atom mean? Atom comes from the Greek atomos, which meant can't be cut down any further, because early Greek thinkers a couple of thousand years ago had the insight to think that the world was made up of tiny things and there were billions and billions and billions of them, but they were so small that they were the smallest thing that could exist, and they called them atoms because they thought you couldn't get smaller than atoms. But in fact, you can get smaller than atoms, because inside atoms are what we call subatomic particles. These are tiny building blocks, if you like, which when they all come together, they make an atom. And we have on Earth billions and billions and billions of atoms. Some of them were here when the planet formed, because they were made in stars out in deep space. Some of them are newly formed on Earth. And you might say, well, how do we make new atoms? Well, that can happen because of a thing called radioactive decay, because some substances are radioactive. They break down, and as they break down, they turn themselves into new forms of atoms. So you can start with one chemical, for instance, one called uranium, and that's a metal, and it spits out some energy, some radiation, and as it does so, the atoms fall apart and they produce smaller atoms like lead. So you get one atom turning into a different kind of atom. So there's two sources for the atoms we have on Earth. Some of them came here and formed the Earth about 4.5 billion years ago, but they were made either at the start of the universe or when stars blew themselves up. And some atoms we have on Earth are made because some of the things that we're here to start with have broken down radioactively and produced new daughter atoms of a different type.
Thank you so much, Raiz, for that question. And we've got a voice note.
Afternoon, my name is Butepo, and I have one question. Is a cloud gas or liquid? Thank you, bye.
Thank you so much. What a good question. Doctor, I get so inspired hearing young people being curious about how things work. So is it gas or is it liquid? And I suspect many of the adults don't know the answer.
Well, I went through an airport yesterday, and I was flying home from the island of Sicily, which is down at the bottom of Italy. And I'd been there for a couple of days, 2 or 3 days, to have a look at some of the archaeology there. And I was told when I was going through the airport that I couldn't take my bottle of water because it was more than 100 millilitres. But I'd frozen the water, and I said, but I haven't got any liquids of more than 100 millilitres. And they said, yes, you have. You've got a bottle of water. And I said, it's not a bottle of liquid water. It's a solid.
Yes.
And they still threw it off and took it away. And I said, they need to learn more about physics. But the answer to the question is that when one looks up in the sky, we have water evaporating from the Earth's surface, from us breathing out water, and also from the ocean, because every square metre of the ocean surface is being irradiated by the sun at about the rate of 1 kilowatt. So there's 1,000 joules per second of energy hitting the surface of the sea, and this is evaporating fresh water from the ocean surface. So if you look at the air above an ocean or a lake or a river, you will see water particles, molecules of water in suspended animation, bobbing about in that air. This rises because it's warm, and the ground warms the air above the ground, and the ocean warms the air above the ocean, and it causes it to expand. It's less dense, so it rises, and it keeps going up and up and up. And as it goes up, it feels less pressure from outside. So if it feels less pressure from outside, the result of that is it expands more. And if something expands, it cools. So as air rises through the atmosphere column, it gets bigger and colder. And eventually, you've got a condition where it's cold enough that these molecules of water that were whizzing around all over the place, very spread out, can get together and congeal and form water droplets. So the first thing that happens is you get droplets, but as they continue to rise, pushed up by rising columns of air, they will get so cold that they will then freeze. And so what you've got at altitude in the sky is you've got ice crystals, tiny droplets of frozen water. You've also got some that are melting on their way down, so there's liquid water. And so you have this equilibrium in the sky of a cloud is a mass of ice crystals, water particles, and some are melting, some are refreezing, and they're all being jostled around, buffeting against each other and against the rising air currents. And eventually they get big enough because they keep on collecting more water onto their surfaces that they begin to overwhelm the force of the air rising underneath them and keeping them aloft, and they fall as rain. And some of them make it all the way to the ground and make us wet, replenish our reservoirs, go into our rivers and give us drinking water. Others will evaporate before they actually make it down to the ground, and they go back up and repeat the cycle up in the cloud again. So if you look at a cloud, you've got droplets of water, some of which are going to be liquid, but much of it's going to be tiny particles of frozen water, a bit like my bottle of water at the airport yesterday.
You sound heavily touched by your experience. I think you need to take it up with all of the authorities to petition that should the liquid be frozen. But they could always argue, but your flight was 5 hours long and at some point it would be liquid.
Oh, probably. But the good news is that because scanner technology has improved so significantly in the 20 years since many of these measures were introduced, they are now on the way out. And we're just waiting for many airports to begin to upgrade their scanners. And once everyone's got upgraded enhanced scanning, which can interrogate the contents of bottles, and you can use the color of light that goes through what's in a bottle to work out what's in the liquid inside a bottle without even having to open it. And this is pretty standard physics, but we can do this in a really practical, reliable, reassuringly safe way now. And so this is going to become de rigueur. When you go on an aeroplane, you won't have to worry about whether you've got more than 100 millilitres in future, because we will have the ability to scan things. We already can, but it's introducing it and implementing it safely worldwide. Once that is the case, you'll be back to being able to take all these things on airplanes, and people won't be able to throw my bottle of water away. Isn't that a wonderful piece of news?
Yours was water. For other people, it was alcohol or perfume. So I'm sure many people are looking forward to that day. Let's go to Mark in the East Rand. Mark, go ahead.
Good afternoon, Doc. I wanted to find out how does a rooster, especially in the morning, knows what time to sound the alarm? Because I tell you what, it's like my neighbor's got some chickens, and every morning around 3 o'clock, 4 o'clock, he's just it's like, does it have it at 10 o'clock? Oh, how
yeah,
Mark,
he has.
Mark, did you just say the rooster says kukulu kuku?
It never misses the time. It's like the moment it does that, you check the time, it's either 3 o'clock in the morning or 4 o'clock in the morning. That's my question, Doc.
Mark, the way they do this is because, in fact, even bacteria have a body clock. Even the simplest organisms on Earth keep time. And they do that because it makes such a massive difference to their chances of success on the planet. Because one of the certainties about life is that there will be night and day, and one will follow the other. Unless you're at the North and South Pole. If you're in extremes, then you do get 6 months of daylight, 6 months of darkness. But in most places on the Earth's surface, you will always have a cycle of maybe varying length, but it will be a daytime and a nighttime. And being able to predict that's going to happen and respond accordingly is the key to your success. So most living things that I've ever come across have some way, even plants, of registering what time of day it is. They have a chemical clock that ticks inside their cells, and that can be a mixture of genes that are being turned on in their DNA and turned off, and they work like a genetic and chemical domino effect, with one chemical turning on the next chemical, which turns on the next chemical, and that feeds back and turns off the first chemical. And this keeps time in a cycle, and it changes the pattern of behavior in cells. In us, we have a structure in our brains, hypothalamus, which is called the suprachiasmatic nucleus. That is our master body clock, and it sends signals to other parts of our brains. It also secretes hormones into the bloodstream, which then visit every cell in our body, spreading the time signature to all the slave clocks around the body. So you have this master regulator clock in the brain. It's the same in birds, and birds are really tuned into this because obviously if they have to fly certain distances, they need to keep track on how long they've been flying to help them with navigation. Food appears at certain times of the day and certain times of the year, so birds are also tuned into it for that reason. So the answer is they have a clock in their brains. The brain is set by the day starting and ending, and refined by other cues around them, but they use it to change their behaviour. It wakes them up in the morning, give them a big surge of hormones, and those surges of hormones then tell all the cells in the chicken's body what time of day it is, and it makes the rooster then start crowing.
Dr. Chris Smith, we're going to take a quick break. When we come back, all of your calls and your questions.
702.
The Naked Scientist.
All right, the last couple of minutes with the Naked Scientist, we go immediately to the calls. Sister in queue, go ahead.
Hi, Relebogile and Dr. Chris. I just want to find out. So usually I would have my radio in my bedroom on, right, listening to 702. And then a minute or so, there will be like maybe somebody's reading the news. But then when I walk to the kitchen to switch on the TV, listening to the same radio station, the same thing I just heard in the bedroom is being said in the kitchen. Where else, when I'm playing the two devices, I'm playing the radio and the TV at the same time, they all at the same level. So whatever is said this side is said this side. It's only when I'm switching on the one after the other where I would hear what was said previously in the one room to in the other room.
Just to clarify,
why does that happen?
Are you saying on the television as in you're watching it on DSTV? Listening,
Yeah,
sorry.
I'm using the 8. Yeah, I'm listening through 8. That's 6.
Okay.
The 856, and then I'm
Yes.
listening on the 7. Yeah, then 702 on the other side in my bedroom, right? So usually we say, okay, let
me get Doctor to help you. Doctor, I mean, I know the answer of this one, but can you maybe share from the scientific perspective where if you're listening directly to the radio versus listening to an app or the website, why is it not exactly in time and in sync?
This is all down to the processing and transmission delay. In some cases, if we take a television program, for example, it's come via a satellite. And if you have to send the signal up into space to a geostationary satellite that's in the same position above Earth all the time, that's a journey, a round trip of about 70 or 80,000 kilometers out into space and back. Plus, you've got the way in which the information is encoded. So when it leaves the speaker or presenter's mouth and goes into the machinery in a radio station or a television studio, you've got to convert this into a digital format and then send it on its journey, and then the person's device at the other end has to receive it and reverse that encoding to turn it back into intelligible speech. This all takes a bit of time. There's latency, and different types of transmission and have different transmission delays and different latencies with the encoding and decoding, which is why you get that apparent desynchrony.
Thank you so much for that question. Unfortunately, we don't have enough time for any more, but Dr. Chris Smith, I'm hoping that next week we can kick off with some of the interesting developments in the science world that even you don't have the answers to while you continue to answer the various questions with the Naked Scientist. There's an interesting one that came through on Twitter. I'm going to save it for next week. Thank you so much for joining us on 702 Afternoon.